KCL when you have the, since we are writing the voltage equation, if you have a current source, then I have this supernodal current equation. Similarly, we discuss the nodal analysis. Nodal analysis, we find the number of nodes and then write the current equation for that particular node. Okay. So here also, since we are trying to write a, yes, since we are trying to write the current equation, if you have a voltage source, if you have a voltage source present in the circuit, how do we proceed further? Okay, so that is using supernodal analysis. Okay, so this is nodal analysis using, nodal analysis with voltage sources. If you have voltage source in your circuit, how do we proceed? Okay, so now there are possibilities like the voltage sources connected between the reference node and non-reference node. So as discussed already, you will have n number of nodes in a given circuit, and we'll be assigning n minus 1 voltages, n minus 1 nodal voltages, and then that plus 1 is nothing but reference node. So we'll have n minus 1 nodal unknown voltages, so that we'll have n minus 1 current equation, solving which we'll be able to find out the unknown nodal voltages. Okay, so that additional one node is a reference node. So here we have two possibilities of getting a voltage source. One is between the reference node and the non-reference node. Okay, this is non-reference node and this is reference node. If I have a voltage source between the reference node and non-reference node, okay, that is one possibility. Okay, so now before we see that, so how many nodes we have here? So here we have 4 nodes, okay, including the ground node. Okay, so this is node 1, node 2, and node 3. Okay, so now we have to write 3 equations, because at each node we will apply KCL and write the current equation. But here, as far as this node is concerned, we have a voltage source. We have a voltage source. If suppose I had a current source here, suppose I had a I had a resistance here, that is voltage source in series with resistance, then the scenario is totally different. I can just convert this voltage source into a current source, then I can proceed as usual, not an issue at all. Okay, but here in the circuit we don't have a resistance. We have only the voltage source, only the voltage source. Okay, so now this voltage can be right, because this is V1, voltage at node 1 with respect to ground is V1. Also, from this given circuit, I am able to find directly V1 is nothing but 10 volt. Am I right? Because the voltage source is connected between node 1 and ground, which is what is assumed as V1. So directly I could say that V1 is equal to 10 volt. So I need not go for finding out V1, because V1 is directly, we are able to find the V1 directly. So this is one case. Okay, what is that case 1? If I have a voltage source between the reference node and non-reference node. In case 2, if I have something like this, if I have the voltage source between the 2 nodes. Okay, so you can just relate it with the mesh analysis. If I have the current source between the 2 loops, if I have the current source between the 2 loops, how do I do the same thing? You can relate this with that condition. Okay, so here I have a voltage source between the 2 nodes. Okay, so here in this case, we will consider this as a super node, and we will write the supernodal equation. And then what do we do? Just by combining these 2 nodes, we'll write another equation. Okay, so if the voltage source is between the 2 non-reference nodes, then we have to apply both KCL and KVL. So here, this is identified as super node. This is identified as super node. So how do I proceed further? Now, just remove this. Just remove this and combine those 2 nodes. Combine those 2 nodes and write the current. Okay. So here, these as per, we'll assume as like this itself. Okay. So this is assumed as the entering current, because here I'm not going to write the direct matrix, no, because for super mesh and super nodal, it's little tricky to write the matrix directly. So I'm going to write the equation and solve it. So I can assume in any ways. Okay. So I assume something like this. So entering current is I1. And then here in this loop, entering current is I4. So I1 plus I4 is equal to the leaving current is I2 and I3. Okay. Since I have identified this as a super node, I'm just trying to combine the current equation for these two nodes. Okay. So that is nothing but this equation, and I can write as usual. So this I1 current is going to be V1 minus V2 by 2. And this I2 current is V2 minus Z2. It's a ground node, no? So by 8. And this current will be V3 minus 0 by 6. And this current will be V1 minus V3 divided by 4. Okay. And then now what do I do with the super node? What do I do with super node? So something like this. I need not go for this itself. Directly I could write, because this voltage is V2 and this voltage is V3. So what will be the potential difference between these two? Since plus is connected this side, so voltage is measured at this node with respect to this node. So obviously this will be V2 minus V3. Since the voltage source is given as plus minus, voltage at this node with respect to this node. Okay, so V2 minus V3. If suppose the sign is like this, then it will be V3 minus V2. Okay, from the KVL, it's very clear. Okay, so I can write the super node. So I have three equations. The first equation is V1 directly 10 volt. The second equation is supernodal equation, that is combining the node 2 and node 3, since I have a voltage source between the two reference nodes. And then the third equation is just write the voltage equivalent of this, that is V2 minus V3 is equal to 5 volts. So now by solving these three equations, I will be able to find out the unknown voltages V1, V2, V3, and whatever is required for the given circuit can be found. Okay.
Ma'am,
So,
could you
yeah.
could you just explain the equation I1 plus I4 equal to I2 plus I3?
Yes,
Sure.
ma'am.
I can't
Yeah,
understand.
yeah. Yes, yes. Okay, no problem. Okay, so here the thing is, this is a super node. Why it is a super node? Because I have a voltage source between node 2 and node 3. Okay, so just if you have understood the super mesh, I'll just try to relate it so that it will be easy to explain. Okay, so what did we do in this case? Just we have removed this current source, which is common between the two loops. I wrote it as, if suppose the current direction is like this, then I1, I2, something like this. So I2 is same as your current source and I1 is opposite to that of the current source. So I can just write I2 minus I1 is equal to this current source value, some value 5 or whatever. Okay, and then what we do? We combine these two loops, right? Same procedure here. So I try to replace this voltage source with the equation V2 minus V3 is equal to 5. Now I have combining the nodes, these two nodes. Okay.
Oh, so V2
So
and
here,
V3 become the same
just
node.
remove this. Yes. Yeah,
Okay.
but the nodal voltages are different. Just remove this.
Okay.
Just remove this and consider the currents present in this node as well as this node. That's why I said here, normally what is the practice I said? Better assume all the currents through the resistors as leaving current, because then only you will get the common conductance as the negative element, right? But here, since we are going to write the equation directly, let us not worry about it. So here, this is assumed like this. So I can say that as far as this node is concerned, one is entering current, the other one is leaving current. That is I1, I2. And as far as the node 3 is concerned, this is I4 entering current and I3 is leaving current. So I1 plus I4, I1 is for node 2 and I4 is for node 3. And then I2 plus I3, I2 is for the this loop, this node 2, and I3 is for the node 3. Okay, just we are combining the currents present in node 2 and node 3. That's all. Okay, so
just want to confirm, since the directions of the current are given, we're not assuming that it's all leading.
no. It's a example problem. That is the reason the currents are given, and I have taken like this. You can assume on your own. You can assume on your own. You can assume all as leaving current. Nothing wrong. Okay, but when finally when you solve, you will get the same value for V1, V2, V3.
Ma'am, is it
Okay, so don't.
necessary that
uh,
at a time we have to assume all as a leaving current and or all as a going incoming currents?
Not at all. Not at all. You can have it on your own, but please remember when I go for a matrix method, just by looking at just by inspecting the circuit, I
Yes.
wanted to write, I want to. Then in those cases, you have to assume clockwise current direction for mesh analysis. For nodal analysis, you have to assume all the currents as leaving current as far as the resistors are concerned. All the currents are leaving currents. If you remember, the
Yeah. Okay, ma'am.
right? Okay, so all the currents with respect to node 1, I assume this as leaving current. But when it comes to node 2, again here the direction I'm assuming in a different way. But then only I will get this common conductance, that is G12 or G21 as a negative value. I will be getting negative value. Okay, so that way it is. Right? Another example. Okay, so this is another example with supernodal analysis. So here I have a voltage source. As soon as I look at I identify the voltage source, I look at the voltage source in the given circuit, then I need to think, what is that? First, I need to think whether I have a series resistance, voltage source in series with the resistance. Then no problem at all, directly you can convert that into a current source and proceed as usual. But here, as far as this given circuit is concerned, we have a voltage source, but we don't have a series resistance. So we cannot convert. So this has to be solved using supernodal voltage equation. Okay, so then now here, if you look at it, this is the voltage source is present between the two reference nodes. Okay, so what should I do now? Now I have to find out as far as the given circuit is concerned, there are three nodes. One is a reference node. So two unknown voltages, V1 and V2. So I need to have two equations solved to find out V1 and V2. Okay, so now since I have the voltage source between node 1 and node 2, and if you refer the polarity for the voltage source plus minus. Okay, so what does it mean? V2 minus V1, V2 minus V1 is equal to 2 volt. Since we are measuring voltage at this node with respect to this node. So potential difference between V2 and V1. And why do we write V2 minus V1? Because V2 is positive with respect to this. Okay, so V2 minus all leaving currents. I assume like that. Not, please remember, it's not at all necessary. It's not necessary that I have to assume this way. You can go for your own assumption. Okay, but I'm assuming all as leaving current. Okay, so now here, as far as this node is concerned, so I have this is entering current. So 2 is equal to this is leaving current. So what will be the current equation? V1 minus 0 divided by 2. Okay, and then in this node, again, I have another current component, current through the 10 ohm resistor. So that is V1 minus V2 divided by 10. Okay, since this is a super node, I have to consider the current components for node 2 also. I'm going to combine node 1 and node 2. Okay, so now let's come to node 2. So now node 2, I have a leaving current 7 amps. So plus 7. And then another current through the 4 ohm resistor, that is again leaving current. So V2 minus 0 divided by 4. Okay, so 1, 2, 3, 4, 5. All the 5 current components are included here in a same equation. Why? Because it's a supernodal. Okay, so now 2 is equal to.
Shouldn't there be six current?
Sorry, ma? 6
Isn't there
currents are.
six? Because for V2, we need to consider the 10 ohm resistance.
See, I have for node 1, 1, 2, 3 branches. For node 2, again 3 branches. But out of the 3, already this current is included, no? So only 5. 1, 2, 3, 4, 5. This is common for node 1 as well as node 2. So I'm considering it as a single current component. If I'm writing it separately, if I didn't have this voltage source,
We ignore V1 minus V2.
What is that?
Ma'am, but shouldn't we ignore this current, which is V1 minus V2 upon 10, because it will be leaving from V1 and entering from V2. So wouldn't its
Correct.
effect be
Same
nullified
term.
then?
Yes, what you're saying is correct. So as far as this node is concerned, it's going to be an entering current. Sorry, as far as this node is concerned, it's going to be a leaving current. So how should I consider? Yes, exactly.
Ma'am,
Okay. Yes, ma'am.
ma'am,
Yeah, I
similarly,
need not consider this current at all. I need not consider this current at all. Sorry, let me correct it. I need not consider this current at all. Why I need not consider this current? Because V1 minus V2 is already written as an equation. The same voltage is going to be present here also, because this is also same. Okay, so this total thing can be removed. This total thing can be ignored here. This total thing can be ignored here because already we have written an equation which is nothing but V2 minus V1 is equal to 2 volt. So now while writing the current equation for by combining, that is just remove these two and combining the node 1 and node 2 in a single equation, I need not consider this. Sorry for this. Okay, so I need not consider. Why I need not consider? Because the voltage across this 10 ohm is nothing but V2 minus V1, same voltage only. Whatever is the voltage between these two, the same voltage is going to be here. So I need not consider this one. I think the voltage sources connected between the two non-reference nodes form a generalized node. We apply both KCL and closing voltage source connected between two nodes and any elements connected in parallel with it. Yeah, see, you can just listen to it. See, so here super node is formed by enclosing a voltage source between the two non-reference node and any element connected in parallel with it. Okay, so I can just, if I have a resistance here, then this is super node, I can just ignore this. So that is the condition. That is the situation here. That's why I took this question. Sorry, somehow I. Okay,
ma'am,
so I can ignore this. Now, is it clear? Let me repeat again. If I have a voltage source between the two non-reference nodes, and then if any element connected in parallel to it, but generally here DC circuit, only resistance. If I have a resistance connected in parallel to it, that is a super node, and then that can be ignored while writing a supernodal current equation. So I can remove this. Yes, yes, somebody interrupted me. Yeah, ask me.
actually we ignore the current through the 2 volt voltmeter, ma'am.
Yeah, why I ignore it? Because already I have written a voltage equation corresponding to this 2 volt source, which is nothing but V2 minus V1 is equal to 2 volt. So here it is not like a normal nodal analysis where we apply only KCL, whereas here we apply KCL as well as KVL. So as far as this portion of the circuit is concerned, we are writing a voltage equation using a KVL, whereas for the remaining part, we are just combining these two nodes and write the current equation using KCL.
Yes, ma'am. So supernodal analysis is applied when voltage source is between two nodes, ma'am.
Between two nodes and between reference node and non-reference node also can be considered as a super node, but that will be very simple. If I have a voltage source instead of this, if suppose I have a voltage source here, then directly, this is also kind of, it's not exactly super node, but here also nodal analysis with voltage sources. But here what can I do? My job is very simple. Directly I could write this as a voltage. V1 is equal to this voltage. I can just skip this node because already I found the value of V1. I can just skip this node. I can proceed with the next node alone. Maybe let's see whether I have. Yeah, see this example. See this example. Okay. Where maybe before I proceed to that circuit, any doubt in this? Any doubt in this question?
No, ma'am.
Okay, good. Okay, so now here I have another example. Find V and I in this circuit. Find V and I in this circuit. Okay, so what is V? V is nothing but voltage drop across this 3 ohm resistor, and I is nothing but current flowing through this 2 ohm resistor. Okay, so if it is given like this, if the question is given like this, then what method do you prefer? You have learned so many methods, source transformation, mesh analysis, nodal analysis. So can anyone answer? What method do you prefer here? Or you can convert this to using series parallel resistance network also, you can reduce the network and you can proceed. Okay. So now the question is, which method do you prefer? Which method is apt to use here for this given circuit?
The voltage and 4 ohm resistors are in series, so we can convert it into a current source and
But this
apply
voltage
super.
value is not. But this voltage value is not given. Correct? This voltage value is not given. I cannot convert, right?
At first, reduce
I
the
do not.
parallel.
Sorry, ma.
At first, reduce the parallel combination into one resistance.
So this you will reduce into a parallel combination. Okay, then so what you do? So I just convert this into a parallel thing. Okay, so because the question is very generic, they didn't specify what method. So in that case, how do you do? That's the question. So for that, you are suggesting 6 in parallel with 2. Just I'll write 6 in parallel with 2, and then here I have a voltage source. How do I proceed further? But the tricky here is I need to find out the current flowing through this 2 ohm resistor. Okay, so now again, I have to find out what is the current flowing through this. From that, I can find out what is the current flowing through this 2 ohm resistor, because these two are in parallel, no? So if I find the current, then that is the current flowing through this parallel network. Then, so total current multiplied by, using current divider rule, I can find out the current flowing through this 2 ohm resistor. Okay, so now I have simplified this network. Then again, what should I do? What will I do to solve this network? Mesh analysis or nodal analysis? That's all. Very simple question. Which method do you prefer here? Mesh or nodal analysis? Mesh analysis, if I consider, then for the reduced network, that is, I have reduced the network by combining these two resistors. I have two loops here. Okay, so I don't have a current source. So directly I could write the voltage equation and solve it. Directly I could write the voltage equation and solve it. Okay, whereas here, when I go for the nodal analysis, see here, this is the first time the voltages are not given. So can anyone tell me how many nodes here? How many nodes here? Can anyone tell me? Let me proceed with nodal analysis. Our discussion is towards the nodal analysis. So now let us proceed with nodal analysis. Okay. So can anyone tell me how many nodes here and which node can be treated as a reference node? Obviously, this is the reference node. This is my reference node. And then how many nodes I have here? These two are one. So node 2. And then this is node 1. Okay, so now should I consider this as a separate node? Should I consider this as a separate node?
The voltage would be V only because one is a non-reference node, the other.
So should I consider, that's all. Let us do it later. But the question is, this is three nodes or only 2 nodes?
3 nodes.
3 nodes. Okay, because this voltage and this voltage is going to be definitely different. So we need to have we need to assign 2 different voltages. Okay, so here, let me sequence Q1, 2, 3. Okay, so now V1 is nothing but V, because voltage at node 1 with respect to ground is nothing but V. Okay, but here the value is not given, unknown voltage. And then here I have between node 2 and node 3, I have a voltage source. So I need to go for a supernodal equation. Can anyone tell me the supernodal? I assume the current direction like this. And what will be the voltage here? How do we replace the 6 volt? Plus is connected towards 3. So
V3 minus V2
very good, is equal to 6. Okay. Now the third equation, which is a supernodal current equation, just by considering the currents present in node 2 as well as node 3. Okay. So now this, since I assume this as entering current, so V1 minus V2 divided by 4. And then this current is leaving current. So V2 minus 0 divided by 3. And then as far as this node is concerned, this is again the leaving current. So plus V3 minus 0 divided by 2 plus V3 minus 0 divided by 6. Now I have these two equations. So now how do I proceed further? How do I proceed further? Because I don't, if I have this value known, then directly I can solve it. If I have this voltage is known, then directly I can substitute here the values. So two equations with two unknown voltages. Okay, so now how do I do? How do I do? Quickly, let's move on to the theorems. Anybody? How do I proceed further? Is it possible to solve this
What if
equations directly?
No, ma'am, what if we apply KVL in one of the loops and then find the value of capital V?
Uh, so you apply KVL here and try to solve this, and you find the value of V. That's what you're trying to say? So,
Yes, ma'am, in the outermost loop.
is this the circuit? Yes, this is the circuit, right? Yeah. Okay, so that is one method. As she suggested, I can just consider this, but here, how do I consider the current flowing through this? How do I consider the current flowing through this? Because it's a common element, right? I cannot simply write, no.
No, ma'am, we'll consider the other loop that is through 4 ohm resistor, then 6 volt, then 6 ohm resistor,
I will
and then back
suggest,
to V.
yeah, I will just suggest another method. So as suggested, I just combine these and I have a voltage source in series with the current in series with the resistor. So what do? I just combine minus 2 plus no. So I'll have the current source in parallel with the resistor. Okay, so I can just root up. What did I do? I have combined these two resistors, or I can have it series also, no problem at all. Okay, so or I can consider this two alone. Anything is fine. So what did I do? I have just combined these two, or you can just consider this alone. Okay, so now I have got this way. I've got this way. Sorry, plus minus. Now directly I have only two nodes now. I have only two nodes now. Okay, I can solve this now. Okay, I have two nodes now. Okay, I think I can solve it now. Solve this now, right? Okay, so just try this question. Just try this question, and
So,
maybe in
ma'am,
next
how
class
do
we
we
will
have
just.
how do we have two nodes now? We still have like there is still a potential drop between the zeroth ground node and the
I have
top
combined
branch.
everything as single one, and I think this has become a single node now. I think this has become a single node now. Yes, correct. Okay, so what did I do now? I will. Is it not going? Fine. Okay, so now I have this. So I just redraw the circuit. What did I do? I have just combined this into a single resistor and I converted this voltage source this into a single resistor. Okay, so this is converted into a current source. That is what I did here. I just combined these two resistors. This resistor is 6 in parallel with 2. That is in series with the voltage source. Now I'm converting this into a current source. Okay, so this is my ground node. Okay, now this is connected to, this is what I have replaced, no? This is what I have replaced, right? So I have a 4 ohm resistor and then this is connected to 6 ohm resistor and I have a voltage source here. Okay, so now these two are same nodes only. So I have only one node. I have only one node, isn't it?
And what about the top left? That is also a node, right?
Yeah, that's what. Since this voltage is unknown, I directly I could write this current, no? Directly I could write this current, right? I consider only one node. I consider only one node here. Okay, so now maybe I will just write the equation. I consider only node
You're
A.
directly writing the nodal equation. That's what you mean to
Yes,
say, right?
I'm going to
Okay.
write a KCL equation directly at node A. Okay, so here I assume all are leaving currents. This also leaving current. So here only all are leaving currents. And what will be this current source value? 6 in parallel with 2 will be 12 divided by 8, which
by
is going to be, sorry, ma, anybody quickly?
3 by 2.
3 by
Point. That's what, 1 point. Okay, 3
Right.
by 2, right? So 3 by 2 multiplied by, sorry, this is a current source. No? So V by R. So what is the voltage value? 6 volt. God.
it would be 9.
6 volt only. So 6 volt only. So 6 by 3 by 2. 6 by 3 by 2. So what is the answer? 6 by 3 by 2, 12 by 3, that's 4 amps. Okay, so this is 4 amps. And this is 3 by 2. Okay, so all are leaving currents. So 4 amps plus VA by 3 by 2 plus VA by, and what is this? 3 ohms resistor, VA by 3 plus, and what will be this current? Can anyone tell me? VA minus V divided by 4 is equal to
4
0.
map.
Okay, VA minus V divided by 4. Why V? Because we have current flowing through this is going to be, I have two voltages. Here I have a VA voltage and here we have another voltage which is a voltage source V. Okay, so now again here we have two unknown voltages. Again here we have two unknown voltages. How do I solve this? That's why I just leave it to you. You try to solve it and let us discuss the answer in the next class. Okay, so I'll just leave this question for you to solve and we will discuss the answer in the next class. Okay. Yes. Okay, I have another example here. I want to move on to the theorem quickly. Okay. So here I have another equation, sorry, another circuit here. Can anyone tell me how do I solve this? So what do I do here? I will
First
just
simplify at the right. First start
that's
simplifying the
yeah.
resistance networks.
Yes. So now this is actually if the question is not about nodal voltage, then it will be easy to solve because only one source I have. I just go for series parallel combination, reduce the network and solve it. But here the nodal equation, it's given as nodal equation. So obviously node 1, node 2, node 3. 1, 2, 3. This is my reference node. So here what I'm going to do. So can I say this current flowing through this 3 ohms and 9 ohms will be same? Current flowing through this 3 ohms and 9 ohms will be same. So what I can do, I can just combine these two and write as 12 ohm resistor. And okay, so I'm just considering this part alone. So I can consider, that is, I can convert this into a current source. So now I have a minus 2 plus, I have a current source like this, parallel with the resistor, and the remaining part of the circuit you can just copy as it is. Okay, so now this will be 12 ohms and this will be 240 by 20 amps. Now I can proceed further. So this is my node 1. This is my node 1 and this is my remaining part of the circuit. This is 6 ohm resistor, remaining part of the circuit. So I have 3 nodes as usual, normal nodal analysis. I have 3 nodes, I can just solve it. Okay, so the interesting thing here is I have combined these two resistors because in this loop or here in this circuit, whatever is the current flowing through the 3 ohm resistor, same current is going to flow through the 9 ohm resistor. But when it comes to 6 ohm resistor, this current will be divided. Okay, I cannot say this is series, but definitely these two are going to be in series. Okay, so I'm just combining these two resistor. That becomes a 12 ohm resistor. Voltage source in series with the 12 ohm resistor is converted as a current source. Now I'm proceeding further with the nodal voltage, with the nodal analysis.
Ma'am, it doesn't matter that the current through 9 ohm and 3 ohm are opposite or the same or same in direction. That doesn't matter, right?
Can you repeat again?
Yeah, I'm saying that we are converting the 3 ohm and 9 ohm to 12 ohm, but it doesn't matter that the current through 3 ohm and 9 ohm might be in opposite directions. With all, in all
It,
probability, they will.
definitely it's not going to be in the opposite direction, no? See, so whatever current, same direction, same current only, no? So it's
No,
not
no,
going to
yeah,
be different
right,
direction.
right. You went in
Yeah.
the clockwise, right, right.
Yes, yes. Because only one source I have. I have only one source. So definitely, as far as this part of the circuit is concerned, I'm going the current is same current, same direction. So no confusion. It's going to it's these two are in series. These two are in series. Okay. This the nodal analysis is over. The next method. So we are going to have circuit theorems. We have circuit theorems. Okay, using circuit theorems also we can solve the network. Okay, so now when this method will be useful. Okay, so now so far what we discussed is analysis of circuit using KCL and KVL. Okay, that is using mesh analysis and nodal analysis. Okay, so that's very easy only. Solving using mesh analysis and nodal analysis is easy, that is without tampering the circuit. What is the meaning of without tampering? I'm not going to disturb the circuit at all. Okay, I'm not going to, I may redraw the circuit, but I may not remove any of the components or open or short anything. So that's fine. Okay, but the disadvantage is for complex circuit, the computation becomes tedious. As discussed, if you have 4 loop or 5 loops, then it's very difficult. Okay, so now generally in application circuits, generally most of them are going to be a complex circuit only. Okay, so now how do I proceed? So to handle this, we have some theorems. We have some theorems, circuit theorems, which can be applied to solve a network. We have some circuit theorems which can be applied to simplify the circuit analysis. Okay, but generally all these theorems are applicable only to the linear networks or linear circuits. Okay, so there are so many theorems available, but as far as our syllabus is concerned, we are going to discuss only the maximum power transfer theorem. Maximum power transfer theorem is basically derived from either Thevenin's theorem or Norton's theorem, but we are going to consider Thevenin's theorem here. Okay, so now what is meant by linear circuit? Because what is that mentioned here? The theorems are applicable only when the given network is a linear network. Okay, so in general, the circuit is linear. If it is additive, that's okay. That's a common property. But here, if the circuit is consisting of only linear elements and linear dependent sources and linear independent sources. Okay, if your source and the element present in the network is linear, then we can say that the given network is a linear network. Or in a simple terms, we can say that the linear circuit is an electric circuit in which the circuit parameters are constant. In other words, a circuit whose parameters are not changed with respect to the load. With respect to the load. Okay, so with respect to current or voltage, that's what. With respect to the current or voltage connected as a load. Okay, so now the circuit, whatever we are going to consider, are mostly the linear circuits only. So now, as I mentioned, we are going to start with the Thevenin's theorem. So plenty of theorems are there, but our focus with respect to the syllabus is only maximum power transfer theorem. Maximum power transfer theorem is solved based on either Thevenin's or Norton's theorem. So we'll consider Thevenin's theorem here. Okay. So now, as discussed, so for complex circuits, these methods may be suitable because using these methods, if I solve, it is easy. Okay, so now in practice or in real time, okay, we may be interested. Okay, we may be interested to solve a network with respect to a particular load terminal. Okay, in practice, in a circuit, the load is generally a variable one. Okay, for example, I have a source. I have sometimes I may be connecting only refrigerator and the other electrical. Okay, whereas sometimes I may be connecting my air conditioner along with that. So my load is a variable one. So with respect to this load, because this is a variable one, no? So what I do, I consider only the remaining part of the circuit and then simplify this as like this. Okay, now connect a load. Now it will be easy, no? So instead of solving this complete network for different load values is difficult. So instead of that, what we can do, just This is my interesting point because with respect to this load only, I want to do analysis. So the remaining network, I will just calculate the, or I will just find out the equivalent network. I will just try to replace this with an equivalent network consisting of Thevenin's voltage in series with RTH. Whereas in Norton's theorem, this remaining network is converted into a Norton current in parallel with the resistance. That's the difference between the Thevenin's theorem and Norton's theorem. Okay, so my interesting thing is this load, because this is going to be variable. So for this variable element, if the load is only 2 ohms, what is the power dissipation for this load? Or if the load is 10 ohms, what is the power dissipation? So that is what is my interesting. What do I do now? So now just ignore this load and remaining part of the network can be drawn with its equivalent network. So equivalent network comprising voltage source in series with the resistance. So this is called as Thevenin's voltage and Thevenin's resistance. Now it will be easy. So instead of solving the network again and again for different loads is very difficult. So instead of that, this is easy, no? Because I have only 2 resistors. Okay, because one is a load resistor, which is going to be variable value. So for each and every value of load, it will be easy for us to identify whether I want to find the load current or power dissipation or whatever. Okay, so this is nothing but the Thevenin's theorem. Now, how do I find the Thevenin's equivalent? How do I draw the equivalent circuit? How do I draw the Thevenin's equivalent circuit? So now, as per the Thevenin's theorem, this can be replaced by an equivalent circuit consisting of this VTH and RTH. Okay, now how do I find out this VTH and RTH? So now VTH is the Thevenin's voltage, open circuit voltage at the terminals. Because my interesting point is this load, no? So I'll just ignore this load because this is going to be variable. So I consider only the remaining part and just remove this load and find out the open circuit voltage. Find out the open circuit voltage. That is nothing but VTH. And then RTH is equivalent resistance at the terminals. Again, at the terminals A and B, equivalent resistance when the sources are turned off. Okay, so now my that is, as far as the application is concerned, I have to find out the I have to do the circuit analysis only with respect to this load because my load is going to be variable. So now the solution is, or if I go for the Thevenin's theorem, what do we do? Just with respect to this load, just ignore this load, consider the remaining part of the network and try to replace it with its equivalent Thevenin's circuit consisting of VTH and RTH. So how do we find this VTH and RTH? With respect to this load. So just remove this load, find out the open circuit voltage. That is nothing but VTH. And what is RTH? Again, with respect to these two terminals, what is the equivalent resistance? By switching off, by turning off all the sources. Okay, so if I have a voltage source, how do I turn off the voltage source? Now, just by shorting the voltage source, that will become 0. Okay, I have some voltage value. So now when I short it, that will become 0 volt, turned off. So when I have a current source, how do we turn off the current source? Just open it so that the current becomes 0. So this way, if I have independent sources, I'll just turn off the sources and find out the resistance equivalent from these two terminals. Okay, this is the Thevenin's theorem. So now it will be easy because I have replaced the complex big network into a simple network consisting of only VTH and RTH. Now for different values of RL, I can find out easily what will be the load current and what will be the voltage across the load and what will be the power. Okay, so now that's the reason we go for this Thevenin's theorem because I have my load variable. So it's very difficult to solve the network again and again for different values of RL. Instead of that, I go for Thevenin's theorem. So that is replace the complete complex network into a simple Thevenin's equivalent network and connect the load now, solve it. Okay. Respect your different circuits we can solve. Probably we'll continue this in the next class. We'll continue this in the next class. Okay, so all of you, please solve this network. Probably I will upload this question, this PPT now itself in Teams. Before your next class, you solve this and come. This network. Find out the V and I. Find out the V and I. Okay. So
Also,
yeah.
ma'am, in our CAT one, we only have module 1.
Module 1, and we have 2 more classes in the next week, no? So by
Right.
Friday, I'll be completing this theorem. So module 1 will be, with that the module 1 will be over. And module 2, I'll just start with the module 2. Whatever we discuss in the next 2 classes, no? So will be, you can just prepare that also for your CAT 1.
Okay. Okay. And in the assignment that you gave, experiment 2 about nodal and mesh analysis, we don't need to write any theory, right? There was some confusion.
Yes, no need to write any theory. Yes.
Oh, thank you.
Anyways, this Thursday is a holiday, so we don't have a lab class. Next Thursday only we have a lab. I think that's the reason I gave the deadline as Sunday. The Sunday.
Yes, ma'am.
Sunday or Saturday, something else. Some dates I have given.
Sunday, ma'am, Sunday.
Okay. So next Thursday we will do the next experiment. Before that, you can just finish it and upload. Okay.
Ma'am,
So,
can you explain the subtopics in the assignment?
subtopics in the sense? For your
Like the
lab experiment.
yes, ma'am.
Okay. So those of class can leave. I have taken your attendance. Those of class can leave.
Thank you, ma'am.
For that experiment, you can just draw the,
Thank
you
you,
can
ma'am.
as usual, ma, objective. Yes, ma, objective, circuit diagram. You have to draw the circuit diagram, given circuit diagram. And then next is theoretical calculation. First network using mesh analysis, second network using nodal analysis, then simulation procedure. Okay. I have
Okay.
I have
Ma'am,
told
should we
you
include
write it in 3 steps. Then finally the tabular column, then result.
ma'am, should we include photos for each step, or is the final
That is
circuit
what
enough?
that's what we discussed in the last class. Procedure, you can just try combine everything as a single step. Draw the schematic, draw the circuit diagram, draw the schematic for a given circuit diagram. You can just include only one snapshot. Then second step can be the analysis. Go for transient analysis and observe the values with appropriate snapshot.
Okay, ma'am.
Okay. Okay. So if there is no doubt, maybe I'll wind up the class. We'll meet in the next class on Friday.
Thank you, ma'am.
Okay.